inviting me back yet again. I'm always surprised that anybody wants to hear what I've got to say, but I'll try and make it interesting. So So the first thing to say about modal analysis is what it is and it isn't. So in fact, modal analysis is really a concept, meaning that you represent how a system's dynamic behavior in terms of a set of modes, which are a property of that system. We can start to say where the modes come from a finite element model, or we can do it from measurements. And even for simple things, you can calculate it on the back of an envelope. So it's a concept rather than a specific activity or single task. Then obviously this is a question that comes up. What on the earth is a mode? A mode. So I don't normally travel by kayak. So I think we get here the first useful synonym really is resonance. So we're already familiar with the idea that various things sort of ring at a single pitch or multiple pitches at the same time. So I think if you blow over a bottle, that's quite a pure sign.
For a refill on a prescription.
Hello?
714.
Is there something I need to respond to?
No, I just have to mute these people.
Okay. But lots of things have pitches simultaneously, and they aren't necessarily multiples of the fundamental, like a string. But anyway, let's not get bogged down. So this is an inevitable question, and there isn't actually a very easy answer, because you need concepts that haven't been yet explained. So the best way is just to start with some things that are kind of familiar. So we can say that a mode is, hang on, I seem to be missing a slide. Yes, got in, that's okay. So I actually meant them to be in a different order, but anyway, a mode which we are in the process of defining is actually defined as a route which expresses the frequency that it happens at and the damping, the rate that it loses energy. And those things are the same for all points measured on the structure, and it's a global property, but it also has a shape. So each point that you've measured has a constant which expresses its amplitude and the phase. So the phase is really its relationship to the excitation force in time. So, and mostly it's relatively simple. It's either happening at the same time in the same direction as the excitation, or in exactly the opposite. There are cases when it's not. It's a little bit off, even sort of 90 degrees out occasionally. But these things, if we don't get if we don't let the new information overwhelm us, we really financially we're quite familiar with resonant systems such as our grandfather's clock here, which is a nice example of a pendulum. And in this one, it's got one of those very sophisticated ones with different metals that make it, even when the temperature changes, the length of the pendulum doesn't change. So the time it takes for the pendulum to complete a swing depends not on the mass at the end of the pendulum, but on its length. And the little sort of watch mechanism in the top right, that was actually ended up as a better solution for clocks used on ships to so you could keep the time accurately over a period of weeks, so that you could use it to check where you are when you're sailing ships, and your check your, never remember whether it's latitude or longitude. And then we should be quite familiar with things like a weight on a spring. We can visualize that. So if the weight starts at its equilibrium position, we can lift it up or pull it down and let go, and then it will bounce, exceeding going beyond the equilibrium position and then back again. In none of these cases do we really need to, we don't really need to create animations of them, because you can actually see it. It's slow enough to see and see exactly what it does. Then a string does have multiple modes on the same system, and they are, in this particular case, because the wave speed is supposed to be the same at all frequencies, then the modes or overtones are very nearly a multiple of the fundamental, and they're always an integer number of half wavelengths. So the first one is approximately a half wavelength, and then you get two of them, 3, 4, 5, 6, etc. So if you look in the little diagram, you can see they've called it a speaker, but I think that's really a stinger. So it is an electromagnetic device that can put in energy at a single frequency at a time, and that allows you to excite the string in these particular patterns. And I think I don't know if they're using a strobe or something, but you can actually get so you can see the shape with your eye. So why do modes exist? In my mind, there are two main sort of strands for this. One is purely about how the number of wavelengths fit into an available space, and examples of that are things like standing waves in a room. And then there's a similar idea. You could apply it to strings and beams, then ultimately to modes in violin plates. Or another way is to think of a restoring force, bringing the mass back to its equilibrium point position and then exceeding it, and a repeating cycle. So that force, that returning force, restoring force, is most often the elastic modulus of all parts of the material in the system. And they therefore also have a time constant. So any of these repeating modes that have a repetitive cycle, that they have a fixed time that takes place in. In the case of the mass on the spring, that returning force is literally the elastic modulus of the spring. So you've neatly separated the two concepts into physically different parts of the little demo. And with the pendulum, it's gravity, and in the string, it's its tension, not the elastic modulus of the string, it's the tension. And air modes, it's the compression and rarefaction of gases. So gases, if you can put them in an enclosed space, you can start to feel its springiness. Like if you put your thumb over the end of a bicycle pump, you can feel how strong the elasticity of the air is. And when we want to look at modes, there's many ways we can look at them. So this, if it's something that's not very simple, like we need to look in terms of plot with nodal lines, as in the bottom left, and then we could, instead of that, we could put color, and then the white bits are implicitly where the nodal lines are. And we could have a static 3D plot, in which case we would have to greatly, in most cases, greatly exaggerate the spatial displacement, whether that represents velocity or acceleration or whatever. And then if we animate them, we're going to have to slow it down, otherwise you're not going to be able to see it. It's too fast for the eye. And even better is if we've got a 3D animated plot that we can rotate at will to choose our view of it at any given moment. And then icing on the cake is 3D animated plots with a fully triaxial response, which we'll come back to that in a bit, but that starts to get expensive and difficult, and that's not going to be one of the things the VSA kit offers. But on the right, I think most of you will agree that that way of representing the mode shape is actually quite easy on the eye to look at and see what it means. And that's done with a few thousand triangles. And the resolution is fine enough that it looks very smooth. Unfortunately, with this, it's a lot more work to set up the animation. I'm working on it. I've been working on it since about 2012 and haven't quite got there. Thanks to Jim, we can see there's a group of animations of beams, each with a different boundary condition. So the boundary conditions are about how the object we're looking at is supported. So if we start with the first one and bring it to life, you can see what it does, and it has nodes. I hope you can see my pointer. We'll have a node there and a node there. But when we, no, I can't do that. Won't let me. I have to. That didn't work. Right. We start this one. Now the nodal points are at the ends. And that actually vibrates at a lower frequency than the one, the free one. So pinned or simply supported basically means that the two ends are constrained in the vertical direction, but otherwise free to rotate at the ends or to expand and contract on the X plane. But when we come to the third one with clamped ends, this one has the same frequency as the free one. But you can see in addition to the vertical motion, the rotation at the ends has been taken out. We move to the next mode. I'm trying to, there we go. So instead of being 1/2 wavelength, it's 2. And the animation runs a little bit faster to show that. So the ends are never nodes in a freely supported item such as a beam. In the case of a plate, you can have a node, you can have nodal lines that cross the edges, but they won't be nodal lines all the way around. In the pinned ones, there's definitely a likeness between all three. In the shape, it's just that the boundary conditions make them just slightly different. Come on, next slide. And just the next one, same sort of thing. So we're representing the beam just as a single line. We're not making any attempt to make it visually realistic. Trying to, oops. This one, these set are actual measured ones. Like I did some time ago, little course for students and makers at Bilbao. And one of the things we did was we measured a beam in different boundary conditions. And the points that we needed to display the shape, we used 18 along the length, but that allows us to see the twist in the beam. So because this was actually a real piece of wood, something like a cello bass bar, you find even at low frequencies, some of that motion that you would think would be just in the fundamental mode, actually a bit of twist gets introduced. That's just to do with the non-uniform nature of the wood. So you should be able to see that these look very similar to the animations that Jim Woodhouse has come up with for us. So trying to keep the mathematics down to a minimum here. The central really to everything we do with modal analysis and vibration measurements involves moving things between the time domain and the frequency domain. And we use, in this black box in the middle, is the Fourier transform. I call it the workhorse of acoustics and vibration engineering. And my little joke at the bottom says terms and conditions apply. So it's actually a very reliable algorithm, except there are some conditions one must observe to get make sure you get good results. And I'll try and cover some of that a little bit later on. So on the chart on the left is a time domain one. That's the typical ring down of when you tap a violin. So it starts with a large amplitude with logarithmic decay. Then you've got a decision like where to chop it off. Like anyway, I'll come back to that. But on the right, instead of seeing it as a variation in sound pressure level plotted against time, we see an amplitude plotted against frequency. So it's very, very important to get this idea that we can move between these two domains. But we're not going to discuss exactly how we do it or the details. Now then, I made a little video here, but there is sound, but apparently it's so quiet, I'm just going to talk over it. So on the in the little pane on the right, you see a violin corpus sitting on a trapeze net, which is a frame with a network of 0.5 of a millimeter silicone thread, which is good because it doesn't keep stretching and it doesn't perish. Probably has some damping. And I have some laser lines which are useful for helping lay out the points. So, okay, so I'm in the process of doing a modal analysis on a corpus without a sound post. As you see, the accelerometer is placed where the G foot of the bridge would be. It's supported on a silicone net. Accelerometer is where the G foot of the bridge would be. Net. The threads are about 0.5 or so of a millimeter of silicone thread. And I have also some laser lines which I can move around as a guide. It helps me place the points. I also have a sheet of paper which tells me where the points are, and I keep an eye on that in case I forget where they are, and keep an eye on the index as displayed on the screen. So I'm currently working on point number 12, which is here. That's Right, so before the George in the video saves it, we can actually see how the screen is now populated. Let me see if I can get the laser pointer. So this pane here, this little chart, actually shows you the time history of the for impact. So that is the force history of the excitation, if that makes sense. So it's like the hammer impulse that Tom showed us in his little talk at the beginning. The reason why it doesn't look like a perfectly symmetrical spike is because it isn't uniform in its frequency content. The actual corpus is somewhat compliant, and it allows a bit more energy in at different frequencies. And then there are other complications, like sometimes that the duration of the contact is long enough that the material is moving back towards the hammer instead of away from it. So in the top left-hand pane, the very top one, the red series, is the time domain, sorry, the frequency domain representation of the hammer impact, which starts, well, I've set the maximum to 0 so that you can see how, reading off the decibel scale on the left, you can see how much the level has dropped. So generally speaking, we'd like to be not worse than -20 decibels, but if the system is low noise, -40 is okay. And maybe a bit even worse, in some conditions, it may be okay to work with it. And in the bottom pane here, we have the time history of the response, that is the signal that's come from the accelerometer. And that has been shown in this window as its spectrum. So this is a raw spectrum that would be, you know, it would be larger amplitude if I hit harder and less if I don't. But we've actually chosen sub-ranges to work with. So if I choose, say, to work with 44,100 samples per second, that means the highest frequency, known as the Nyquist frequency, that I can view is 22,050, which is okay. That's I certainly can't hear that high. And although I don't need the data that high, I want to be sure that the signals that I'm processing don't contain information near that frequency, because otherwise it could corrupt some of the frequencies lower down. And I always choose 24 bits, because for using up 50% more RAM, I get a 256 factor improvement in resolution, which wouldn't matter if the signal was all like it is at the beginning here, reasonable, you know, 50% of the available dynamic bandwidth, absolutely fine. But in fact, because the signal decays, there's a point at which it merges in with the background noise. And we could have some quantization errors from there. That is, that the sound card is not able to differentiate well between very low levels. And we choose the data length is the 32768. For the fast Fourier transform, it's a special version of the algorithm. It needs to be a power of 2. But I pick out a sub-range of the frequency. I just discard everything below the green line and everything above it, because I don't need to save it. The data's not useful. And in here, I don't want to see the full time window, which is about 0.7 something of a second, I think. I just want I want to see the hammer, and I want to see just a little bit after it in case I've missed a double bounce or some other feature. And for the response, I think for a violin, well, I tend to be working with 0.4 of a second at the moment, but 0.3 will do. If you come down to 0.1, I think there's some other problems that can arise from that. So as we move to the right of the screen, this is where we're looking at the data that we actually want to keep and process. So you can't only see a bit of this window, but the green series, no, the orange series is the current FRF, and it's not exactly how it's done, but just for now, this description will be near enough, is to say that the transfer function, which is a ratio of the response to the excitation, is achieved essentially by dividing the response by the excitation in the frequency domain, which then becomes arithmetically a simple task. Computers are very happy to do that. But the green one is an average, a running average of those FRFs. So we hit the same point multiple times to try and reduce noise. So here in this top right pane, the kind of greenish color is the frequency response function, or FRF, that we're wanting to save. And the purpley blue series is what's called the coherence, which basically tells us how alike all the captors are to each other. So if, for example, I hit the wrong side of an F hole by mistake, that coherence would really drop down terribly. It tends to be poor anyway in the very low frequency range, possibly for some of the reasons we were discussing earlier, that the performance of the transducers, very low frequency, is not so good. And perhaps we weren't actually able to put all that much energy into the system down there. It tends to be bad anywhere where there's anti-resonance. So that's a position in the spectrum where the stuff above and below adds together in such a way as to create a null. Again, it'll be poor higher up if this response from the hammer drops too low, or if we get a deep notch, say from a double hit, we may have very poor data. These are things we have to work around. I'm going to try and restart the video.
Everything looks reasonable.
I'll just let it run just so you can just see the process and write your questions down for later.
Point 14 is halfway between here and the corner on the edge.
I can set up a pair of rulers on the sides of the net in order to
okay.
actually just look at that.
Is pretty bad high up.
Notch in the hammer signal.
With an edge point. Point number.
If I set up rulers, I can actually read the laser line rule, even on the ruler, and I can place the points.
Every single point sounds different.
At least I can put a laser across.
One way of making a
better
mistake.
accuracy than a millimeter.
You find you're hitting the same point again.
Better than a radius of about 2 millimeters around the point.
And so on.
That's that. So
okay, so I'm in.
This graph is from FRFs collected at that Bilbao training course. And what I've done is I've taken an average of points 1 and 2, 3 and 4, 5 and 6, because they're next to each other along the length. And if I do that, then the twist component gets left out. We don't have to think about it. Interesting to note that the first mode, everything goes in the same direction. So whether if this shows negative here, it means in our plot we will see the deformation going downwards from the equilibrium position. If it's positive, we'll see it going up. So the first mode of a pin beam, everything goes in the same direction, but in the second mode and upwards, roughly half go in one direction and half go in the other. The first three modes are nicely separated and they're quite easy to work with. But by the time you get up to the much more difficult to process region here, it's going to be relatively difficult to fit the modes and be sure what we've got. And this is an experiment, so just for the moment, just focus on, let me get my laser pointer back. Let's focus on the first mode, which is in red. Now, there's no significance to these colors. They're just a set of colors which make it easier on the eye to pick out one curve from another. So if they're all the same color, it would be more confusing. So what I've done is I've laid out these FRFs in space, roughly in the position as they would be along the length of the beam. So in order to get what I would call an operating deflection shape, which is not in any way processed, that's just the raw data from the collected FRFs. There's been no attempt to take account of the influence of other modes on the one we're looking at. So it's not quite zero at the end, but nearly. So that is precisely the shape that we see when we look at that mode. And if I move to the next one, which is the green, let's follow that along. That's the 2 half wavelengths, like a whole sine wave. And the third one has 3 half wavelengths, and the fourth has 4. So I'd like feedback on this diagram as to whether or not it helps people to whether it helps people to understand it. So,
I like that a lot.
Thank you. That's helpful. Right. So this is a little bit of a review of what we've done so far. To say that we have easy systems, things like pendulums, weights on springs. Then we have a little bit more complicated things like strings and beams, which so long as we consider a single polarization, that's we're only looking at one plane at a time, then we have, we can call that a one-dimensional system. So our displacements are Z values along an x-axis, if you like. Then we move to flat plates, but they're beam-like, but they have sets of modes in both directions. So we'll call that a two-dimensional system. That is, the location of the Z displacement is on the X and Y plane. So X and Y take you to the point that has that particular displacement, and the Z is how far it is above or below the surface. Then we move to arch plates. They start to get harder to understand because it's no longer satisfactory to represent them solely with one displacement value. That's because an arch spreads out as you depress it and shrinks in as you lift it up in the middle. So it's more of a conceptual challenge. And this is a 3D system, but not easily represented from uniaxial measurements. We move on. If we have triaxial measurements for each point, we have a full 3D representation. And that's the kind of data we see in the STRAD 3D project. And it is necessary, we need to see it, although it's not available to us all the time. And then we move on to an assembled instrument with strings. It's complicated because primarily it has this shell structure, It's already been perturbed with a sound post and to a lesser extent a bass bar. Makes less difference, you think. It has enclosed air. It has these substructures, neck, fingerboard, tailpiece, bridge and strings, and a support system. We unfortunately need that because we don't have access to a space station to do these measurements in zero gravity. Right, this is as mathematical as it gets. So let me get my laser pointer back. So typically we call a transfer function h. It's just a convention, and it's at frequency lowercase omega, and that's because the mathematicians and physicists like to think of frequency in radians per second. But for our purpose, it wouldn't matter if I just put an f there in hertz. So that's to say that we have a mode 1. Mode 1 is actually here at about 240 hertz or something, or whatever it is. There's modes 2 and 3 are close together at about 430-ish. And mode 4 is little perturbation, which is actually the A1 mode, so on. Then we're saying, in addition to the modes that we've identified in the range that we're analyzing, we have to take account of anything that's below that, if there's anything that's contributing to the overall spectrum below that range. So if I shouldn't be anything much here because that is the first mode, but if I'd started up here, then I would need to, when I fit these modes, I need to make some kind of provision for these 4 modes below. And then there's everything that's above. So in theory, the system could have an infinite number of modes, but they will be at very, very low amplitudes. So each mode, if you looked on a linear scale, you'd see it would look like it went to pretty close to 0. But it shows more on a log scale. But if you add up 20 modes, 50 modes, 100 modes, that residual from them is quite considerable and needs to be taken into account. So I hope I've said enough about this. And these are the six modes from that. So this is that corpus that I was measuring in the video. And the fitting slide that we've just seen is the same data. And these are the 6 modes that we take out of it. And these are the 6 modes that are features of a corpus without a sound post and without a neck and fingerboard. The convention is to use names like the ones we use for the assembled instrument, which is a whole history behind why they've got their names. But if we use a lower case, we say, well, this is an ancestor mode, because it's not quite the same shape, because it doesn't have a sound post. But this pair basically are, the kind of real motor behind them is internal air, which interacts with the walls of the shell or the corpus walls. So the A0 is at a lower frequency than it would be if the walls could somehow be made infinitely rigid. But the actual shape of this longitudinal dipole shape of the corpus is actually a property of the corpus, but you don't usually see that until around about 850 hertz. So I think anyway, that's enough on that one. So B1 minus is very, very similar to A0. There's a little bit more of the corpus bending in it. There are reasons for that. We needn't go into that. CBR is a twisting mode of the whole corpus and is not really involved in radiation unless it has significant asymmetry, which sometimes it does. But these pair actually are very interesting because they're they're not like what we see in the instrument with the sound post. So we have this big transverse dipole. Now sometimes it's locked really into the island and the lower bout, and doesn't really penetrate into the upper bout very much. And sometimes the amplitude in the back is very small. This one, I don't know whether it's a good thing, I hope it is, but it actually uses up, this dipole spreads out most of the plate, and the back is quite active. Then a little bit higher, you can see that this is just a pure anticlastic bending of the corpus. But when we put the sound post in, somehow these two get, it's probably not quite the right way to describe it, but it's sort of partly right. They become the B1 plus mode with this rotation of the island being forced to be asymmetric, and then it's combined with this anticlastic bending. So I'll just pop back a second. So that one is A0. This is B1 minus CBR, A1, transverse dipole, anticlastic bending. So what I was saying about arched plates really is not been quite satisfactory to look at them in just with one displacement axis. So you can see here that in one cycle, each of these plates has a width change component. That width change is coupled via the rib structure, so that even though this behavior of those plates like this is there are, before the corpus is assembled, they're approximately 100 Hertz apart, they actually couple very, very strongly. And if there's a slightly less of the back than there is at the top, which is normally the case, this will then lead to a corpus bending component, but still mostly breathing with a bending component. But if I put the two, if we're what we call anti-breathing, the both plates go in the same way as in that mode that I called anticlastic bending, I think it was at 619 Hertz, their width changes in opposite, top and the back change in opposite directions. So this causes the anticlastic bending. So in these two plots, I've not put in any edge clamping effect, but in this one I've added some edge clamping. So I've used this nice Galleria Estense pictures. Thank you, Zanre and friends. And here is a fully 3D model with triple lasers showing an A0 mode. And here is my static plot, which shows the same thing. So if you look, you can see the width changing quite clearly. And you can see a small bending component along the length of the corpus. I hope that's clear. And this is also done in the Aztec facility, but it has bridge and strings and everything. And we're looking at the B1 plus mode, which is one of the combination of the anticlastic bending of the corpus and a breathing component. So as the C bouts move upwards, the back bulges out, and the island rotates. The G foot is lifting as the same time as the back bulges out, pivoting on the sound post. So this has significant volume change and is a good radiator. On the right, but just to remind you, I put the transverse dipole and the anticlastic bending shapes in the static version. So I think these two show you that anticlastic bending quite well. And this one shows you the width change. We've got more of these, which we can come back to at the end. So each one of these lasers costs about £100,000, and the robot. So it's big, like a human standing here would head would come up to about that level. It's a big thing. I mean, this would be in more than 100,000. The whole facility was about 2 million. They all sit on seismically isolated blocks. Didn't work out, unfortunately. They had to shut it down. This one, I've shown this one before, but this is a nice animation because it's a CBR from the Titian Stradivari. All I've done is I've used the software provided on the DVD and the data, and I've made up my own animation. I've chosen my view and the way it's presented, just to sort of make it easy to see the three-dimensional nature of the mode. So what is it for? Well, I have to get rid of the, can't have the, unfortunately I can't see my pointer while I'm doing this. There we go. Well, what I think it's most useful for is understanding how violins work. When I say violins, I mean also violas, cellos, basses, viola da gamba, anything like similar instruments. I think it's very useful for understanding how they work. That is, by looking at the mode shapes, we can understand the different radiation mechanisms at different frequencies. So I don't think we can put a price, we can't really fix a value to that. To me, it's invaluable. We can get a global sense of the instrument's character, whether it's how it is because of its very light, stiff wood, or because it's got crappy, heavy wood with high damping and not much stiffness. So it's to some extent a diagnostic tool. If we perceive deficiencies in the instrument, we can maybe track it down to something. At least we can look at things, we can find better candidates for what we might want to change. And it's an indicator for general acoustic health. And I've had people come to me and say, George, I've just made this violin, it's okay, but it just sounds a little bit peculiar, you know, what should I do? So just occasionally, if I've got time, I will do the modal analysis. Then I can turn around and say, well, quite often it turns out that I'd have to say there's nothing really wrong with the instrument. Everything is doing what I expect it to do. I would just be a little bit patient, give it a little bit more time to settle, do a bit more adjustment. I think you'll find it will be okay. And that's usually what happens. But if there's some serious acoustic health problem, then we, you know, I'll be able to say, well, you're not going to fix this by moving soundposts and trimming bridges or changing the strings. None of those things are really going to impact it. We're going to have to go in there deeply and take the instrument apart and do some bigger changes. It leads us to understand which things about our design and the way we build them, which things are important. And it's become, I would say, an essential part of controlled experiments, which is how we become better makers. I don't find it actually useful in adjustments. I think the sound of an instrument and its playing feel, they are simply better assessed by playing and listening. But if I identify if we identify a problem from playing and listening, I can go back to the sound radiation measurements and the structural measurements, and I can say, well, I think that simply that back's too thick. We're going to have to thin it out a bit. It doesn't guarantee you success every time. And it's not a way to quantify quality. By that I mean, like if we ever got to the point where when you submit your instrument for a competition, if then people did modal analysis on them all and rated them on that basis, I don't think that would be helpful at all. Because in the end, it's what it's like to play and listen to. But these other things are to help us get there. So how we're going to use it in our work is, well, we get our hammer and our accelerometer and our software. We go out Strat hunting and Del Jesu hunting, measure them, and then say, we'll make one like that. So that's a tonal copy. Martin Schlesker did this for a while. He had a degree of success, but I think in the end he felt that he was better basically understanding what he wanted his violin to be like and using his knowledge from modal analysis to achieve those goals rather than cloning an existing instrument. Well, we've got a record of our own work, so the next time I make a particular model, I can go back and look what I did the last time and say, well, what might I want to do differently? And we document the working steps so that if I have an issue with it and I want to come back and think, well, what could I have done differently? I've actually got an awful lot of information. And the working steps are basically graduating the plates, which I do in steps, and I might have target weights, target frequencies, and characteristic impedance. So it's not really making by numbers. So although I can get the same characteristic impedance value with different weights and different frequencies, it's not the same thing. So I would say that there are minimum, well, there's a sort of maximum weight I'd want to work with in plate. I don't really want a plate with a bass bar that weighs even 68 grams, although I find a lot of old instruments that do have plates of that weight. And I don't really want it with a bass bar on to be less than about 56 grams. And I don't want my mode 5 at the top, I don't want that to be before the bass bar. I don't want it to be 380, and I don't want it to be 280. So it's looking at a number of things at the same time. So I'm looking at the impedance, but I'm asking, how did I get there as well? So that will affect my judgment as to whether when I'm graduating a plate, whether I've reached an end point or not. And if I haven't, well, I can always open it up and take a bit more out. Then we add the bass bar and trim that down. Then there are various sort of things one could follow for that. When we close the box, now suddenly everything is different. Those free plates behave in an entirely different way. And I put the sound post in. Now I've enforced asymmetry and added the neck and fingerboard. Quite a bit changes, and now it's a lot more complicated system. So if I go back and look at as the box was when I closed it, then as I accumulate that data, it's like having free plate data but better. Yeah, so each of these things we add increases the complexity of the system. And although, yes, I do want to look at the system as it is when it's played, it's not necessarily the easiest way to understand the kind of character of the instrument. And I can adapt as we proceed, which is, I think we would all want to do that, wouldn't we? That leads us to some things that we've not necessarily paid attention to. So one of the things that came up, not just my work, this also includes Colin Goff's work with his shell models and things. So we find the island, it makes sense that the island is an important design parameter. So it's, to some extent, it's like a little rectangular plate with its own localized modes decoupled from the rest of the plate. Not completely, but somewhat. And those, its properties will in fact affect its modes, and therefore it will affect the control, the performance in way rather similar to how the things like the bridge rock and bounce control performance. So when we think about F-holes, we think about the shape of the F-hole and how they look sort of sitting there on the top. But in fact, another thing they're doing is defining the shape and dimensions of the island. So we're interested in the width, the bridge position, the length of the F-holes, space between the upper eyes, which is where most of the decoupling takes place, the graduation, and as an example, we see some Del Jesu models with very long F-holes, with big wings on them, and say early 1600-ish sort of Amati instruments with relatively widely spaced F-holes, very short, like say violas with violin-sized F-holes, minimal wings. And then the edges, which I've been mostly making them to standard dimensions. But in fact, if we think about this degree of clamping around the edge, if we go back, if you can remember those three animations I showed of the plates changing width as the corpus breathes. So we can see that behavior of those edges is important. It's very crucial for that coupling. So the outline itself actually creates a bit of clamping, because if you think of the C bouts of three sides of a box, there's already some rigidity in that as a unit. Then there's the thickness at near the lining, there's the lining dimensions, and there's the rib thickness itself. So there are a number of things that take place in the way that the rib garland glued to both plates creates boundary conditions for both plates, and each plate is a contributor to the boundary conditions of the other. So that these various springiness characteristics of the ribs, I think, are something to pay attention to. And in this plot, I've plotted the top and three plates, top and back, by mode, so these don't necessarily exactly coincide. But one can see that once you close the box, which is the green series, that the damping goes up, and that's A0. So that presumably has got something to do with the air going in and out of the F-holes. And overall, the fact that it's higher damping is probably to do with that, rather than the fact that the edges are glued to the ribs. I hadn't wanted to include this, but this is the pinned edge rig for holding the plate in this condition where the edges cannot move in the vertical direction. This is in French, and this particular plot, they're a bit small, but what they show is these are average frequencies of frequency mode 2 and mode 5 of free tops and free backs. They're various colors, so they're averaged, and these little error bars show how much variation there was. So there's a medium step here where before the bass bar is glued on, and then after the bass bar. So there you can see the mode 5 goes up quite a lot after the bass bar is glued. Well, we know that. Here, for some reason, these Victor and Joseph wanted to include the back in a half graduated state. I think it would have been better to leave that out. So that's anyway, that's the way they've done it. And on the right is the same information, but with the pinned edge condition. And in the middle there, the empty corpus, empty shell, as Colin likes to call it. So it's corpus without a sound post and neck. And there's the full instrument with the error bar. So I wanted to show you this just to help you understand what you're looking at, but it's this next run that is interesting. So in the Bilbao experiment, all the plates were cut on a CNC machine to be as dimensionally identical as possible, and we selected the wood to be as identical as we could get it. So here this is the Comparative is the standard deviation, and we divide by the frequency, because otherwise 10 hertz at 100 hertz is small. I mean, the actual variation in frequency looks, if it's 10 hertz but it's at a kilohertz, that's nothing, but 10 hertz at 50 hertz is significant. So we see, as in this, the intention was to make the plates different. So that's as we expect. There's large differences between the tops, between them well, they started out the same. By the time they finished, there's large differences. So this one is that same plot, but these are the 6 violins made in the school, with very carefully controlled. And these are another set of violins made by external makers. And the first thing we can see is, in fact, although dimensionally all the plates were similar as they were for the school 6, the variation is much greater. That means that the external makers were either unable or unwilling to select wood within the density parameters that we had suggested. Now, whereas in the school instruments, the differences get much larger as the work proceeds, because that was the intention. It's the other way around with the external makers. They tend to converge towards more similar results. So looking here with the so yes, we're looking at the corpus without a sound post and the full instrument. So the actual differences become rather less. So compared, if we look, we have some modes difference. This standard deviation over frequency is in excess of 10, but by the time we've assembled the instrument, it's only about 2, with the exception of CBR. Now, in all cases, CBR is the mode that has the biggest variation. This last set is doing the same thing, but with the pinned edges. So we're starting out with the stuff all looking very similar, but we don't get the same degree of variation in the pinned edge condition as we do in the free plates. And likewise in the school ones, they started out, the external makers started out with bigger variations, but it ended up with smaller ones. So, but there again, that's just saying the makers were compensating and adjusting for the materials that they're working with, whereas this set of school instruments were deliberately going in the other direction. But it's a little bit of a surprise to me that the CBR is the one that has the biggest variations. You've probably all heard the wisdom that the B1 plus is a tonal barometer. I think maybe you need to come back and think about how whether CBR is significant in some respect. Right, we're getting in.
I may, George, if I may, I'd like to add something here.
Yes, please
Just
do.
looking at the frequency, okay? So we are not looking at amplitudes. So all this is about the frequency of the modes.
But there's a tendency for amplitude to go up as the frequency comes down, as a general thing. But you're right. We're only looking at the frequencies.
And just to clarify for everybody, but we were very surprised to see if you look at the school violins, the middle plot on the right, so that's the full instrument, and we were very surprised that we ended up with so little variation between the instruments. That's quite amazing, and even for the school violins,
because I mean we had very large differences in the plates.
Yeah. And even for the school violins, you know, except for CBR, we are less than 2%, which is very surprising because everything was made to have like very different violins, or very different plates, I should say. And we end up with very similar violins in the end. And that's, I think, there was a bit already shown by, what's his name? Martin Schleske. He made one article in the Catgut or the VSA paper that it was trying to follow the modes of a full experiment, and he concluded that as well, that there were less differences at the end than what you could have expected from the plates. But interestingly, when we look at the pinned edges plates, we have something which is closer to the final picture than when we look at the free edges plates. So that's maybe an indicator that measuring the plate with pinned edges conditions may be more interesting than with free edges.
I agree. I mean, I'm continuing to work on it, but it's not without its problems. Yes, I mean it's remarkable in the external makers how, what's that one, the green one? That's that B1 minus. Hardly any difference at all. Anyway, we've got a little run of thinking stuff, and then it's all pictures from then on. So we have this sort of diagram. Let's down here where we have this is the workshop, it's the bench, and we've got a drawing board and we design instruments and we select our materials, build the damn thing. And over here, we evaluate the instruments. So that's listening and playing. We do that to some extent ourselves anyway, but then we've got the acoustic measurements. Now, how do these three zones interact with each other? So I'm building it up in bits. So if you're a research lab or you're making with a bit of technical skill, and we're all going to be doing it now with the VSA modal analysis kit. So we can draw the connection between the constructional parameters and the acoustic measurements and sound radiation. There is a causal relationship there, but to connect with those evaluations by listeners and players, we actually have to have psychoacoustics. But as makers, we try to short circuit that. We will just play them ourselves and try and make judgments. So our designs, they might be very simple, or they might be elaborate meshes on computers. It's not so difficult at all to learn to do these measurements. Learning how to interpret the information is something else. But as we can always improve our skills as listeners. So one of the things we do, in training courses and workshops that I do with Claudia, we always do listening tests, but not just as experiments, but as a training to help people be more sure about what it is they're hearing. And finally, we'll say, well, definitely there's a causal connection. If we have that, well, that connection tells us that something needs changing. This area here tells us possibly what it is, and then we can go back and redo the work here. Along here, well, we want fairly kind of empirical visceral experience, an intuitive relationship between things that we do with our sharp tools and the end result. But here, this part of it, ask Claudia, she's here, the whole business of trying to get meaningful information about how people perceive instruments is fraught with problems, because you cannot measure humans in the way that you can measure a structure. So you have to set up experiments, and you have to statistically process the responses that people give. So it's difficult, but it's not without some success, I would say. Progressing. Now then, I can start to relax now, because it's just pictures. What I've done here is I've taken the operating deflection shape of the fundamental G-string pitch of a violin, then I've added 5 harmonics. So the first harmonic is half the amplitude, the second, third, the next one a quarter, and so on. And they're in opposite, each one in opposite phase. So I just sum them all together. So this is an interesting question about domains. So if I hit my violin with a hammer, all the modes of the system all ring down simultaneously, and the motion is going to be very complicated and pretty well impossible to understand, which is why in the first instance we split it out from the time domain and into the frequency domain, where we can look at it at one frequency at a time or a single mode at a time. But here I've gone back a little bit into the time domain. It's like saying, well, if I was bowing this note, the input from the bow is approximately this sawtooth, and we can see that actually the movement is far more complicated than we would normally see in a modal animation. And I've got a diatonic scale here. Sort of there's a little glitch at the end of the cycle. I haven't been able to track down what causes that. I think you can see, if you look at the back, you can see a certain amount of CBR there. It's actually there in the top as well, but it's easy to see in the back. So is an animation in the frequency domain or the time domain? So in a sense, it's both, isn't it? It's somewhat in the time domain. It's definitely originates in the frequency domain, but now it's also in a spatial domain. So we play the A. Still some CBR there, but some other things. We start to see the scroll twist come in. B, lot of tailpiece activity. Now, I don't want that tailpiece activity too high. It can be a nuisance. But now we start to see we can get very high velocities, particularly at F-hole wings. The C, so we're getting towards A0. So pretty complicated. The G, once again, because that's close in frequency to the CBR mode, it's dominated by that. Does that make the tone better? I think probably not. It's could give a risk of some wolfiness. Anyway, that is the end of the talk as prepared. So I'm going to stop the share for now, and then we can come back and decide what if we want to see some more animations, or whether we've got full-blown argument is going to break out.
All right. Thank you, George.
Okay, you're very welcome.
You packed
I
a
think
lot.
wasn't much over time. I was slightly
No,
over
but
time.
you packed a lot of stuff in your talk. So
Yeah, I did, yes. If everybody's a little bit tired, you could just take a.
uh-huh.
You can't see me. I'm doing a bit of Tai Chi breathing to feel calm.
So if you have a question or a comment, please use the raise hand feature. And if you can't figure out how to use it, you can always type something into the chat. So let's start with Anders.
Yeah, hello. Thanks for an interesting talk. Do you hear me?
I do. I hear you fine.
Okay, I have several questions to you, but I will start with the one I think is most interesting for everyone, really. And that is, you spent a lot of time showing motion in the seatbelt area and in relation to the modes, sort of a 3D understanding of what happens around the B1 plus, for instance. And I wonder, since you put a lot of emphasis on that, and you also said things towards the end of the talk, do you use the rib area there and the listing and or the thickness of the plates in some specific way to improve the breathing motion there, or has those model shapes, when you have learned how they work, have they influenced your making?
Yes. Is that one question or is it several?
Yeah, it's probably several, but I can't control myself. Sorry.
Yeah. Let me think how to answer that. Well, I would say that if you went back and looked at some of those 3D animations, actually it's all of the ribs are participating in the breathing effect. Yeah. So there's expansion all the way around, but it's more across the seatbelts than anywhere else. And that makes sense. That's because that's where the arching is highest, isn't it? So you would expect that width change to be greatest where the arching is highest.
Okay,
but
so
then
should
the
it be
arching is the same
stiff
height
or
along
soft?
the length, isn't it? So so the corpus can bend in a way that perhaps is non-intuitive. In fact, if you consider holding the two end blocks rigid, the seatbelts can move up and down together. So yeah, I think you can get breathing that is mostly to do with that part of the structure. So I would say perhaps this is a reason. I think this is one of the reasons why the corners of violins are not insignificant, in the fact that they're corner blocks, and that the edges are thick in the corners, and they very often thicker around the seatbelts than they are in the upper and the lower belts. And I think that is partly because that helps to preserve the right angle. But then that right angle, that is, when you look at the animations, 3D animations of the CBR mode, you can see the shape of the seatbelt itself is causing this sort of edge clamping and compelling it to act together as a single block. But in terms of, I think more and more about linings, and I take more care to set them make them at a height that I decided that I wanted them. So I mean, like, it's quite easy when you slap them in, you can have some bits, the lining is actually taller in some places than others. So I'm trying to get that more even, get the shaping nice, and then all of these things, you want enough, but not too much. So you want your ribs thick enough to be springy and bendy, but not so thick that they are over rigid and constraining the motion. And likewise with the edges, you know, they do you really want their edge to taper down to a minimum? Because I think if you did that, you might get the kind of waves on the beach effect, that the waves in the plates will slow down as they reach the edge, and the energy will tend to dissipate. Whereas actually, if the edges are a reasonable thickness, then the energy will transmit through the ribs and around the corpus. I think I can imagine that there are people who don't entirely agree with that view, but anyway, it's certainly something to think about, because I think there isn't really I don't think it's in dispute that these coupling of the plates through the ribs are very important to the behavior of a violin, you know, the shell model, how it behaves. I don't think that's in dispute. Exactly what one should do to get particular results is a little bit more complicated.
Can I ask a second question?
Ask Van. Yeah, I guess.
Go ahead.
Okay, thank you. I wonder, when you do the mode fitting, do we get out the effective mass of each mode then?
Yes.
Okay.
The effective mass is the inverse of the accelerants.
Okay.
And the impedance is the inverse of the mobility, and the spring stiffness is the inverse of the I've lost the word at the moment. What the hell is it called? Somebody help me. The frequency domain name for spatial displacement.
Acceptance.
Acceptance, yes. I never thought I'd forget that word, but they're a useful set. So you could, up to a point, you can take that information from an FRF, but when you fit a mode, it's by default it's receptance. But you can very easily convert in the frequency domain. You can convert between receptance, mobility, and accelerants purely by integration and differentiation, and that's simply multiplying by I omega, or dividing by I omega. So that's, if you don't understand it, don't worry, and Anders does.
Well, I'm trying to. Yeah, that was like, I have another question, but maybe it's on the same line. If you do, can I go on?
See the other hands raised, so why not?
Yeah,
go
nobody
ahead.
else has their hand raised.
Okay,
So
I'm
keep on
scaring
going,
away
Anders.
everybody. Okay, and that you showed some slides with where you commented on. You showed the Jim's animations of that bar clamped and pinned and free, and I wonder. And you seem to be a bit occupied with the clampiness, sort of violin plates around the border.
Yes.
Is that something you will see in the effective mass of the modes, or volume production efficiency?
Well, there is one observation about the clamped edges is that if you have an arching with recurve, you get more width change for the height change than if the edges are able to rotate. And the reason is because if the edges are free to rotate, while you're I can't demonstrate it because my camera isn't working, but the central part of the arching spreads out like pressing a frisbee on a table, but the recurve part is folding while you're doing that and going the other way. So, but if you clamp the edges, it means that the recurve part also expands and contracts with the central area.
Yeah.
I know. Well, you need to see some diagrams and animations if you don't believe that.
So,
But,
so George, maybe we should back up one step and maybe two steps for a lot of this audience, which is back one step is, are violin edges mainly clamped or pinned? And actually, fundamentally, why are we interested in clamped or pinned, you know, versus free plates?
Because the violin, their edges are somewhere between clamped and pinned. So while the edges are somewhat mobile, but there's a tendency for the edge to preserve that right angle. So yes, I think this is taking us in the direction of understanding the boundary conditions of plates on assembled instruments.
You know, it's a very typical or common thing to do, I think, with all the instruments also, to double the edges when there are wear too much.
Mm.
Do
I
you
think
think
it helps to do that because there's so much wood kind of broken off and so many crumbly bits that there's nothing really left to glue properly. I don't know that they do the edge doubling for acoustic reasons. I think most restoration doesn't think about the acoustics at all.
Yeah, so I think one of the obvious points, which maybe not everybody is, we should probably emphasize more, is that a lot of the measurements have been done on free plates. Number one, and number two, Claudia did mention Martin Schlesky's landmark paper from I think this is probably almost 2 decades ago, where he followed the evolution of the modal frequencies and found that in the end it didn't vary that much despite what they did. So I think the point there is that I think your work in trying to measure, for example, clamped plates, is to see if the measurements on the clamp plates are closer to the end instrument and would be more useful than the measurements on the free plates.
Yes, I think we've shown that they are closer. Well, the mode shapes, for a start, the mode shapes are like the ones that we see on the assembled instrument. Not exactly, but very much closer.
But closer. All right, so John, you're muted.
Oh.
George, thank you as always for getting the thinking going. Two comments. One is that, you asked for how people liked the diagram where you connected the modes to the waveform, to the wavelength, and I have to say that that was fabulous. And one of the things I'm doing these days is teaching high school physics, and that's exactly I've actually been showing modal forms for students and helping them understand vibration, sound, and so on. And a graph like that is fabulous. That's the kind of thing that I always search for as a teacher. So thank you.
Well, feel free to copy it, or you can ask me to send you the picture if you want. But
yeah, I might follow up.
My first attempt at it, it's quite difficult to set these up. It takes quite a lot of work to get everything in the right place, and so another time round, I think I can do a better picture.
Yeah, but I think it's a great track.
It shows you one mode at a time, maybe, because
I think it's a great track to go down because it helps to connect how the plate is vibrating with what the data that you're seeing from the from the hammers from the instrumentation is showing. So that I think that's could be very, very useful in lots of ways. Same thing with boundary conditions. That I think you're saying, there's this, it's, the plate is somewhere between fixed and mobile, right? And I will just say anecdotally that I found that in guitars, I've been experimenting with building small guitars. And why is it that small guitars seem to be very loud? They seem to be actually quite efficient. It seemed that I've been using thin sides, flexible sides. And that seems to, again, this is observationally, I haven't been empirical about this, to actually increase the perceived size of the instrument. It sounds like a larger instrument, and my sense is that we're essentially the plate is actually sort of borrowing from the sides, and we're also being able to get more volumetric change. But that's just to add to that notion about the impact of the sides and the stiffness of that interface. So anyhow, just an observation.
Are pretty standardized, aren't they? And I think, you know, a small difference in the rib thickness on a violin isn't a massive difference in sound, but still it's part of the way the system works, and we shouldn't just ignore it as being irrelevant.
And also the notion that, you know, guitars and violins are different systems, and, you know, guitars don't have, you know, corner blocks and other things like that, that sort of really.
They don't normally have the back and the front don't have synchronized breathing.
Correct.
So if they,
well, sometimes they do, but they're in efficient modes. Yeah, right.
It's often driven by the kind of bridge end of the top of a guitar, isn't it?
Yeah. Yeah.
But then you might well find that that's coupled to a longitudinal dipole in the back, and there isn't actually a single breathing mode, which is a property of these instruments with two arched plates.
Absolutely. Thank you.
Well,
All right, thanks, John. Joseph?
Well, first, thanks, George, for the super interesting talk. I'm curious, does your software allow you to predict the net volume change for any given mode?
Yes.
And do you do that routinely as a way of estimating the radiation?
Yes.
And can you also do the same thing? Like, would it be average surface velocity or something at higher frequencies? There's some way of getting a general radiation pattern and comparing instruments from the modal analysis?
Any of those things. Well, you know, there was a previous talk I gave where I showed you that I could extract the volume change, but I could also extract longitudinal and transverse dipoles from either the whole corpus or the upper or lower bout.
And so have you actually created graphs comparing instruments in that way from the modal analyses?
No,
I mean, kind of
comparisons other than with volume change. I have compared a number of instruments, their volume change components, but I haven't applied all the different types of dipole and so on to that.
Okay, and what
is
is your
exercise? We could relatively easily do that sometime.
So, I mean, as I understand it, in principle, you could get the radiation from a sufficiently accurate modal analysis. Correct me if I'm wrong, but it's probably difficult or impossible to do. How far do you think we could go?
I'm not sure this is really my specialization, but I mean, if you ask the question, what is the average surface velocity, then I can probably give you a reasonable estimate of that.
And well, maybe Jim could connect the two. Is surface velocity at higher frequency related to the total radiation?
Something like that. Evan might be more able than me on this. He's there. Are you listening, Evan?
Yes, I'm here.
Oh, sorry to wake you up.
Oh, yeah. Well, you got dogs in the house, so I wanted to keep it quiet. It gets complicated in a hurry, I guess is the right answer. There is an expression that relates the local vibration levels to the sound radiation, which will give you the directivity pattern and the power output. It becomes a heavily computational problem and very sensitive to small variations. And so we can have two extremes. In the low extremes, we have the volume displacement. As much air as you pump gives you kind of a very strong source in the low frequencies. In the high frequencies, it's kind of an energy argument that the mean squared velocity across the entire surface is an indicator of how good a radiator you're going to have, but it also has a radiation efficiency, which for a complex object is actually very complicated to compute. So you can use these as kind of general trend type things, kind of the skeleton curves that both Jim and I use to give you a trend line, but to get the specifics out, it's a really difficult problem. So if you have a, this is kind of where, even if you just stick in computational land to do a finite element model, the coupling to radiation in a 3D object that's kind of self-venting, the FO gives us some nice numerical problems up at the open box. It's just a very unstable calculation, and I don't know if it's particularly meaningful. It is one of the problems with acoustics is you can write down the equation, but to actually do the real problem is a numerical headache. Thanks.
And just, so lastly, George, when you're doing modal analyses, let's say you haven't actually played the instruments, that I imagine that's true, but do you think you can get a sense of the overall tonal character? I mean, are you developing an intuition that way?
I could get an idea of some of the gross features. So, for example, if it's strangled up in the low frequency and lots of energy in the top, I'll be able to see that straight away, or the other way around. I think and then one can look at the general levels as well, whether it's going to be quite loud or not. But I don't think I can get really much, even from looking at a sound radiation spectrum, I can't really get a walk away with much sense of its timbre, whether it's a beautiful instrument or anything like that. I only really rather simple, basic features.
Thank you.
All right, Peter?
Yes, thanks, George, for a very illuminating talk. I just have a couple of questions. There was one of your animations. It was the one that you had done, taking the numbers from the Strad 3D project. It was a green animation.
Oh, yeah.
I think it was around 400 hertz or something like that. Was that a dipole mode? It wasn't.
No, it was CBR mode.
Okay, CBR. And when you were talking, I'm not sure if I understood you correctly. Did you actually say at some point that some modes contribute something or they don't contribute something?
To radiation.
To radiation, and that would be basically the amplitude, volume. Is that it?
Well, the thing about CBR is it's a left-right anti-symmetric mode. I mean, and that means that it tends to cancel, the two sides cancel each other out. It's a poor radiator. I mean, it's often visible in the spectrum, but but other times it gets mixed with B1 minus. That's due to coupling with substructures, and then you get versions of CBR that have quite a lot of volume change. Then it is a radiator. But in fact, what is basically happening is the volume change component that belongs to B1 minus is being shared out. So you don't actually end up necessarily with more of it. You just end up with a different distribution of it. So it would always be good if you get more, but and it doesn't actually seem to, you might think, oh, well, nice to have it spread out in, more lower peaks rather than one really big one. But it doesn't seem to make that much difference to the perceived character of the instrument, whether CBR is a radiator or not.
So it could be actually contributing significantly to the characteristics of the instrument, although it wouldn't come out just in volume then.
It can certainly contribute to the playing feel. I mean, I had one instrument I used to look after was about a 1680-ish Pamphilon violin, and it had a really big CBR around about F natural, and the F natural was Wolfie. So it's still affecting the mobility at the top of the bridge, whether it radiates or not.
Okay. And when you say it has a bit of a cancellation characteristic to it, I can sort of see that in a local way, but perhaps it radiates left and then right, and so it's like they don't do it at the same time. Is that possible?
Well,
that
the contiguous areas are not big enough to be radiators without cancellation. So basically, the air just moves from one to the other. So, say if the E side of the instrument is creating a positive pressure, the G side will be creating a negative pressure, and air will just move from one to the other, and not radiate very much.
Okay, so that's on the exterior as well as the interior. Sorry.
It's difficult to find if you've got a mode that actually vibrates at all. It's bound to radiate something, but it's an awful lot less than a mode that's efficient because it has volume change. So basically below about a kilohertz, it's only really the volume modes that have volume change that are good radiators.
Okay.
But it maybe starts to maybe a longitudinal dipole by about kind of 900 hertz maybe is effective. Difficult to say. I don't think anybody really knows.
Yes, they do.
With confidence that the volume change is very important aspect of the low frequency radiating system.
Okay, thanks.
Okay.
John Bean, you asked about the CBR in the chat. Did that discussion answer your questions about the CBR?
Pretty much. It's just sort of, it seems to be a basic right-left flexing. Is that what, if I were to explain CBR, say to me, what would I say?
George, can you explain CBR in very simple terms?
Yes.
What?
George.
Oh, you want me to explain it?
Yes, please.
Yes, please.
Let's see if I can find you an animation.
Yep. Can you find one?
I'm hoping I can.
So while George is finding the animation, there was a previous questions about trying to please review what the modes are again, the super basics. My recommendation is to go watch Jim Woodhouse's videos on our Oberlin Acoustics website, and I think that would be very helpful. All right, George.
I'm trying.
Oh, okay.
It's been. So, people talk about shear in the CBR. So you see the two plates crossing over each other around the C-bouts. Do you see that? If I put my, get my pointer. See here, they're crossing over each other. At least they appear to be when you look there. But if you look at this one, see how that C-bout is rotating as a unit. And then it's taken up simply by twisting the ribs in the upper and lower bouts. So there's no actual in-plane definition of the ribs necessary for this to happen.
And it's important because it affects playing a major role. So I'm wondering.
Well, I think mostly not, but I definitely have come across one instance of that being the case.
Yeah.
So this is the empty corpus. I maybe find it for you. So here's with the neck and strings. So actually, that one really shows you. So that the G side is going towards the back, and the E side is going the opposite way. So it's left-right anti-symmetric. That is to say that the the left side does exactly the opposite of what the right side does. I mean, although CBR isn't especially, it's not really an important radiator, it is an important mode for seeing how the corpus functions. It's a very good example of the 3D behavior. So if you like, the corpus bending that you see in a little bit of it in A0 and in B1 plus and B1 minus, they're in fact like a symmetric version of this type of rib motion.
Yeah.
So if I go, so here's a B1 minus. And then, actually, this is a better version of it. That one was a coupled version. Interestingly, see how much of most of the activity is taking place on the G string side, expansion that way. And it's the top is the major contributor to the volume change. But when we get to, well, this is the longitudinal dipole. That's basically because the walls are interacting with A1 of the enclosed air. And then the B1 plus, you can clearly see the corpus, but as the ribs come up, see it's pinching the back across the waist, making it bulge out. Does that help?
It helps.
Let's go back. Just go back again to see.
Yeah, it's a lot to understand how the affect sound, because I'll see a lot of twisting, and then I'm not sure exactly what that's going to do to what.
I think to look at mode shapes, you need a toolbox, of component motions. So that's why I keep saying things like corpus bending or CBR twist or this, that, or the other, or longitudinal dipole, transverse dipole. That's because these are conceptually easy to visualize. But in fact, the more complicated mode shapes can be built up out of parts that are relatively, in themselves, not so difficult, but difficult to conceive of all at once.
Great.
Everything everywhere all at once.
Great, thank you.
You know what I'm talking about. Some of you obviously do.
Yep. All right. So back to Anders.
Okay, thank you. I wonder, George, which version of your programs do you recommend that we use now? I guess depend on the
ones.
Sorry?
The most recent ones.
Okay.
Well, I keep making changes, but there's some quite big jobs in the programs that need, I need to immerse myself in it for weeks, and I actually want to change the platform. I want to move to everything done on a FireMonkey platform, which will run on Macs and Linux and even Android phones. But I need to do that. I want to use Delphi as the visual interface for designing the programs, but I want to do the mathematics with Python. So it is possible to integrate Delphi, which is in the form of RAD Studio. It's an Embarcadero project, but that can actually integrate with Python. So it sounds simple, but actually I've a long way to go before I'm able to port all my programs to that. But the advantage would be that other people would be, a lot more people write Python code than program in Delphi, which is, it's only Object Pascal. I mean, it's perfectly harmless, straightforward language, but not many people use it. But Python, there's just so much open source free stuff out there that it makes an awful lot of sense to to do a lot of it that way. So you find in universities and places, all those students always used to use MATLAB.
Yeah.
More and more they do everything in Python.
Yes. Thank you.
All right.
Okay.
Any additional questions? If not, then we'll let's give George a great round of applause. Thank you so
Thank you.
much.